My name is Professor Orata. We are continuing with our thermodynamic lectures. Today we look at Carnot Cycle. Carnot Cycle has four processes. We have an isothermal expansion, we have a diabatic expansion, and we have isothermal compression and a diabatic compression. So in the pressure volume diagram, we can represent the Carnot cycle PV, can represent it as follows. So state point 1 to state point 2 is isothermal expansion. State 2 to state point 3 is a diabatic expansion. State point 3 to 4 is isothermal compression. And 4 to 1 is a diabatic compression. So in the Carnot cycle, we are using the ideal gas. That's gas which obeys the ideal gas equation of state PV is equals to nRT. Very important for us to note that. So that when we go to the first law of thermodynamics, from first law of thermodynamics, remember du is equals to dq minus dw. And when we are dealing with Carnot cycle, and we remember that for an ideal gas, remember for an ideal gas, Joule's experiment, we know that du was equal to Cv dt because the coefficient del u del v of t, once again, we said is 0. Remember, this quantity we determined by having a flask which is filled with gas expand into an evacuated flask in what we call free expansion, and we found that those quantities W and Q are 0, so that this quantity del U del V of T was 0. So for ideal gases, we can assume that du is equal to Cv dt. And we mentioned that that is not true for real gases. Real gases, then the story changes. Because in ideal gas, one of the shortcomings that experiment was that we use water whose heat capacity is relatively high, so even if heat was generated during the expansion from the filled to the evacuated flask, you could not detect it. So for ideal gases, du is equal to dCv dt is pretty accurate. So we can replace du with Cv dt, so that Cv dt is equal to dq minus dw. If we integrate this expression over the Carnot cycle, then we will get Cv dt minus is equals to integral of dq minus integral of dw. But dw, remember we said is minus pdv, and we can bring in the expression dw, remember, is minus pdv, and we have said that if the gas is ideal, then P is nRT over V dV. So we can use that expression there and eliminate T by dividing throughout by T. So that we now obtain our expression, integral of Cv dt over T is equals to the integral of dq over T. This is integrated. That cycle means we are integrating over the whole cycle, so that Cv dt as 4 line integrals. That's CV dt from state point 1 to 2, CV dt from state point 2 to 3, CV dt from state point 3 to 4, and CV dt for state point from 4 to 1. So the same applies for dq and dw. So these particular integrals are cyclic integrals, and each of them consists of 4 line integrals. So we have minus integral. We now have integral of nr. We have nr dv over v. We have nr dv over v. And like I said, the integral cv dt over t is the same as the integral from 1 to 2 of cv dt over t. The line integral cv, that's from 2 to 3 cv dt over t, plus the integral from 3 to 4 cv dt over t, plus the integral from 4 to 1 of cv dt over t. Now, if you look at the Carnot cycle, we say that the process was isothermal. Let me just draw it so that I don't lose you. Just draw it here again so that you can always refer to it. Let me not erase it anymore. So let's just have it. That's our Carnot cycle. Remember, 1 to 2, 3 to 4. This is isothermal, expansion, adiabatic, isothermal, compression, adiabatic. Just leave it there, hanging on there, so that tea time you can keep looking at it as you work to that. Now, from the process 1 going to 2, from state point 1 to 2 is an isothermal process. So we can say that corresponds to some temperature TH, and that some temperature TC, a lower temperature, that's a higher temperature. Therefore, T1 is equals to T2 for the isothermal process. And for the isothermal compression, T3 is equals to T4. So already you can see that T1 is equals to T2 is isothermal dt is 0, and for 3 to 4, for 3 to 4, again, that is 0. So those integrals have already vanished. They're already 0. And so in the same way, if you look at T1 and T2, this corresponds to TH, let's call it TH, temperature, the higher temperature, and this corresponds to the lower temperature, TC. Then if you put in the expressions, if you relate these two in terms of, if you relate the two, for example, from 2 to 3 and 4 to 1, where you replace them with the TH and TCs, you are going to see that these particular two integrals will also vanish. So that the cyclic integral CV dt over t will be 0. Will be 0. But that's just one of the integrals. Let us look at the other integral. Let us look at the other integral, cyclic integral of nr dv over v. Again, that is the cyclic integral 1 to 2 nr dv over v plus 2 to 3 nr dv over v plus 3 to 4 nr dv over v plus 4 to 1 nr dv over v. Now, if you go back to our earlier lectures on adiabatic reversible work, we saw that the relationship between volume and temperature for an adiabatic process, and the adiabatic processes are the process from 2 to 3, that's adiabatic expansion, and 4 to 1, adiabatic compression. So for these adiabatic processes, the temperature and volume, we said, are related as, that is T2, V2 gamma minus 1 will be equal to T3, V3 gamma minus 1. And T4, V4 gamma minus 1 is equals to T1, V1 gamma minus 1. Remember, gamma, repeat, like we did in the earlier lecture, was Cp over Cv. So when we use these particular expressions here, we can use them to relate the temperatures and the volume, and you are going to find that when you use these particular quantities, for example, you realize that T1 is equals to T2. So if we have T2, V2 gamma minus 1 over T2, V2 gamma minus 1 divided by T1, V1 gamma minus 1, that will be equal to T3, V3 gamma minus 1 over T4, V4 gamma minus 1. And you notice that T1, T2 are equal because it's an isothermal process. T3 and T4 are equal. And so you can plug in those values. It now relates the volumes. V2 relates V3, V1, V4. So if you plug all that expression based on those simplifications, then you will find that again, the cyclic integral NR dV over V also equals 0. The cyclic integral there also will be 0. So what are we left with? We are left with the cyclic integral. We are left with the cyclic integral dq over t. But again, remember also this cyclic integral as the following integrals 1 to 2 dq over t plus integral from 2 to 3 dq over t plus the integral from 3 to 4 dq over t plus the integral from 4 to 1 dq over t. So if we call this temperature, like we have said here in the PV diagram, in the pressure volume diagram, we call the temperature, that's the higher temperature 1 to 2, and the other one is the lower temperature, Tc, the lower temperature Tc. So we have that integral, we have those integrals where we now have T1 and T2 represents the higher temperature. So we are saying that temperature 1 and 2, we can represent that as higher temperature TH. Temperature 3 to 4, we can represent that as lower temperature, that's 1 and 2, higher temperature. Tc for the lower temperature there, so that is TH, this is Tc. But remember, these are adiabatic processes, and like we have said, for adiabatic processes, dq is 0, so that is 0. For adiabatic process from 2 to 3, that would be 0. And from 4 to 1 will be 0. So what are we having? So we are having the cyclic integral here, dq over t is simply qh over th plus qc over tc. Now, remember we don't have delta q. Like we had said in our earlier lectures, we don't have delta q because q is a path function. So when you integrate, you don't get delta q. But if you integrate du, you get delta u. You integrate dh, you get delta h. ds, you get delta s. That will be the difference. For example, dh, delta h will be final enthalpy minus initial enthalpy. But for q and w, I repeat, q and w, that is heat and work, are path functions. These are found in our earlier lectures, path functions. So when you integrate q, dq, you don't get delta q. There's nothing like delta q. You just get q. Just get q. Very important for us to note that. That's why we don't have delta q, we just get q. So this expression here, remember now, the total integral for the Carnot cycle, which we had said was Cv dt over t cyclic is equals to cyclic integral dq over t minus integral of nr dv over v cyclic integral. You have seen that is now 0, that is 0. So what we are saying is that the cyclic integral dq over t is equals to 0. The cyclic integral dq over t is equals to 0. So it means that is equal to qh over th plus qc over tc. Now, when we are dealing with an heat engine, which is the one characterized by the Carnot cycle, We have a hot body or a reservoir at a higher temperature, and we have a cold body or a reservoir at a lower temperature, and we have the heat engine, and which does work. So heat will be supplied from the hot body, and heat will be discarded to the cold body. Why are they called reservoirs? Why are we calling them reservoirs? We are calling them reservoirs because these temperatures are not affected whether you remove heat or whether you add heat. So they are reservoirs. They are stable relatively under these temperature subtractions and additions. So that the efficiency of a process, as you always remember, the efficiency of a process will be the work output divided by the work input. So that what is our work input and what is our work output? So we have minus W over the input, that's QA, that's the efficiency. And now we see that in our system here, we now see that if you go to first law, du is equals to dq minus dw. We are already seeing that in our system, W here, where you have our du and our dq, remember if the process is adiabatic, that is 0, we have work here and we have du. Now from our system, what we are getting is that we have QH plus TH plus QC over TC, and that is the expression which we are having in our system here. Because remember, that is 0. So that minus W is equals to QH plus QC. QH plus QC. And so we can put in terms of the efficiency there that E is equals to QH plus QC over QH, which now, if you divide the QH over this, is QH over QH plus QC over QC over QH, that is 1. So we end up with 1 plus QC over QH as our efficiency for that Carnot cycle, which we have there. And of course, you can express it in terms of temperature, because you can see that you are able to relate. You can relate temperature to Q. Remember, you can see that we can relate temperature to Q. We can use that small space there. We have QC over TC is equal to minus QH over TH. Of course, you can put the temperatures together, TC, and we'll have minus QH over QC. And you can use that expression there. That is, if you have now QC over QH in terms of temperature, just invert them. That will be QC over QH is equals to TC over TH. Plug in the temperature there, and you get the efficiency in terms of temperature. Now, there are limitations with this Carnot cycle for the heat engine, in the sense that, one, when we are dealing with the expansions in pistons and so forth, like we talked about PV expansions, where we have the piston. Remember, one of the assumptions we said about the piston was that it had no mass, it was massless. We assumed that it was perfectly fitting in the piston cylinder. We had said that it is rigid, the piston is rigid, so it's not collapsible, so that we don't have volume changes. And we also said it is frictionless. That is where the problem is. Frictionless. Getting a frictionless process is a nightmare. So there will be frictional effects, which, because the amount of work done is normally very small, will significantly affect the work, the amount of work. Work quantities. And then the second catch in this Carnot cycle is that following an isothermal expansion with a diabatic expansion is another challenge. Diabatic expansion is another challenge. So these are short limitations involving the Carnot cycle. And we are going to move on to other cycles like the Rankin cycle in our lectures, and we're going to see how these things interface. So we'll stop at that particular point.